Hello, and a very warm welcome to everyone joining us for today's Select Science webinar entitled Enhancing LC-MS Analysis of Oligos, Peptides and Glycans Using Hybrid Surface Technology. My name is Matt McArdle, and I'll be moderating today's presentation. I'm delighted to introduce today's speakers joining us from Waters Corporation, Principal Scientist Jennifer Nguyen, Associate Scientist Jacob Kellett, and Senior Scientist Dr. Xiaoxiao Lu. Today, we're going to be discussing how the performance, sensitivity, and reproducibility of oligopeptide and glycan analysis can be negatively affected by metal interactions. We'll explore the advantages of a new hybrid surface technology for LC hardware that can mitigate these metal interactions and improve reproducibility, recovery, and peak shape. And finally, we will look at gaining a greater understanding towards the necessity of a pump configuration that can deliver accurate and reproducible gradients at low flow rates. After the webinar presentation, we'll move on to our question and answer session. Please feel free to ask any questions for the Q&A session at any time during the webinar. You can submit your question at the left of your screen. Just click on the purple tab. There will also be poll questions appearing after each topic covered in the webinar, and you can take part in these by clicking on the polls as they appear on your screen. Without any further delay, I'm delighted to hand over to our speakers. I want to thank them all for presenting to us today.
Thank you for the introduction. My name is Jennifer Nguyen, and I'll kick off our webinar for today on enhancing LC-MS analysis of oligos, peptides, and glycans using hybrid surface technology. On our agenda for today, I'll take us through an introduction to nonspecific binding, and I'll introduce our primary technology, which has the benefits of max peak high performance surfaces, and I'll show how these benefits can be employed towards enhancing oligonucleotide separations and bioanalysis. Jacob will take us through improvements on peptide mapping using primary technology, and then Xiaoxiao will finish our webinar with glycan analysis. To begin with, what is nonspecific binding and why is this a problem we're trying to address? Well, nonspecific binding, it originally comes from ligand binding assays, this definition, but really in a broader definition, it's any binding of our analyte that is unintended to exposed surfaces. And with this absorption to exposed surfaces, we can lose our sample. So this creates lower sample recoveries, which could affect our chromatographic analysis. So you can see some examples of chemical interactions that can cause nonspecific binding, and also some ways in which scientists seek to suppress nonspecific binding, some of which we'll discuss in the next few slides. Expanding upon nonspecific binding for liquid chromatography, many of us know that acidic inlets in particular disappear during analysis, and this is because of the metals that modern LC columns are made with. Either stainless steel, titanium, and any other metals can lead to this absorptive loss. And these metal inlet interactions are driven by Coulombic attractions such as electrostatic or Lewis acid-based type attractions, which are typically much greater than the polarity-based attractions. And so the result is that we can lose our inlet peak or only retain a portion of what we inject. It can also, as you can see on the right, lead to poor peak shape and also poor reproducibility. As metal inlet absorption has long been a historical problem, there are ways in which analytical scientists take to try to avoid these interactions to get consistent results. And the first, as shown here, sample conditioning is probably the most popular technique, and it's basically making multiple injections of sample or a high mass load injection of sample to saturate any potential binding sites within the column and the LC system to prevent absorption of the inlet. So this can work well, but it can require significant time and effort, and it's not a permanent solution. We've also found that it can take many injections to actually reach our expected recovery. So other techniques as shown here, many of us are familiar with adding additives to our mobile phase, but oftentimes that can create ion suppression. there is a possibility of LC conditioning with phosphoric acid, but it's also not permanent and time consuming. And then if we look at the bioinert hardware such as PEEK columns or titanium, titanium is still a metal, so it can create absorption losses. And PEEK columns, there's limited peak pressure and chemical compatibility. Over the past couple of years, we've worked at Waters to find ways to mitigate these interactions. And because we're a chromatography consumables company, we looked at trying to refine the column and the LC surface technology to address this. And you can see on the left, the figure shows negatively charged functional groups getting absorbed onto the surfaces of traditional metal-based chromatography systems. And the right shows what we introduced to address the problems of nonspecific binding metal inlet interactions, which is the MaxPeak high-performance surface technology. And this technology is a hybrid organic inorganic silica surface that is designed to mitigate unwanted metal surface interactions. And as we'll see later in the slide deck, we've seen significant performance advantages associated with this surface technology on both the column and system hardware. And we'll talk about this in respect to oligos, peptides, and glycans. Before I move on to showcasing some of the benefits of the MaxPeak high-performance surface technology for oligos, I want to point out that the product line that consists of this MaxPeak high-performance surface technology is the Acuity Premier solution, which consists of the Acuity Premier columns and the Acuity Premier system, which you can see here. And within the solution, all metal surfaces in the fluid path are largely non-reactive, and they're highly durable surfaces that are able to withstand very demanding LC-MS conditions and applications. And so this solution, in essence, delivers preconditioned fluid paths that stay well-conditioned and deliver high sensitivity and reproducibility, especially for these inlets that are prone to metal interactions. So let's move on and see what benefits the Acuity Premier solution can give to oligonucleotide separations. And here I just have a brief background slide that indicates that some biomolecules, especially those that are more acidic in character, are more challenging to separate due to its pronounced metal inlet interactions. And we can see that oligos are one such compound, and this is because they have a phosphodiester backbone, which is very prone to absorption to metal surfaces. And then if you have modifications to this backbone, such as a phosphorothioate modification, these are known to be even more challenging to recover. As an example to showcase the benefits of the MaxPeak surface technology for oligo separations, here are some example chromatograms from the separation of the MassPrep oligo standard, which is a standard consisting of 15 to 35 mer oligodeoxythymidines using an Acuity Premier column versus a conventional BEH column. And you can see that the conventional BEH column shows loss of the oligos due to metal hardware absorption upon first injection. So we can't even recover the 15 mer, which comes out first. It's only after conditioning this column with the high mass load of oligo that we can get full recovery of the sample. However, when we use the Acuity Premier BEH column, we get full recovery upon first injection, and the percent RSDs are quite consistent from injection 1 to after conditioning this column, so not much change at all. Here we have a second example of the benefits of MaxPeak for oligo separations, and we're using a phosphorothioate oligonucleotide, GEM91 here. In the previous slide, we used a poly-DT standard, and because this is not a modified oligo, it should be quite easier to recover than this oligo we're looking at here. But we know from the previous slide that we still saw some recovery loss using conventional columns. And here, using the same very similar experimental conditions where we're looking at the first injections of the columns before conditioning with a high mass load injection and then looking at it afterwards, we see a very similar trend. So with the standard column, which is on the left, we see that the peak recovery, the oligo recovery after conditioning is much greater than before we conditioned this column. However, when we compare it directly against the Acuity Premier column, we see that the after conditioning injection of the standard column does not even match the first few injections of the Premier column, which is consistent with its injection after conditioning. So here we see that in this chart to the right, we see that the Acuity Premier column is very consistent for the oligo recovery from injections 1 to injection 5, which is after conditioning. But with the standard column, we see it continues to increase over time, and even after conditioning this column, it doesn't reach the level of the Premier column. And I've tested this a bit longer than the injections as shown here, and it took me at this mass load about 500 injections for it to reach the level of the Premier column. And in some cases, it's quite possible that it may not reach that level. As we've seen, sample loss for oligos can be fairly pronounced using conventional column technology. So to elaborate on the benefits of Premier for calibration curve generation, we ran a few systematic experiments to evaluate the improvements in GEM 91 recovery when using conventional column with a conventional LC system, Acuity Premier column with a conventional LC system, and then the Acuity Premier solution. And prior to this data collection, we conditioned each of these LC systems and columns with multiple injections of GEM 91. And here you can see that the conventional setup yields the lowest recovery as determined by peak area when we look at this dilution series here. The recovery increases when using a Premier column on a conventional system, but the greatest yield is actually produced when using a Premier column and a Premier system. And you can see that this enhancement using Premier technologies also grants a lower limit of detection and lower percent RSCs throughout the dilution series, which aren't shown here. Going into a bit of a deeper dive in this data, you can see that the calibration curves of each of these series are shown to the right. And this is to demonstrate the dynamic range of each of these assays. But when we plot the calibration curves of each data set in a single plot, we can see different slopes of each curve, showcasing the differences in analyte recovery even when the columns and systems are previously conditioned. And you can see that even though the curves appear linear and the R-squared values are quite close to 1, if we plot each data set independently and scale the plots to show the lower mass loads, the data for the conventional column and system lack linearity through the low mass data points. So the recovery and thus linearity can be improved by using a Premier column and conventional system, and is best when incorporating this total Premier solution. And this solution offers the best linearity throughout the dynamic range and also gives the lowest limits of detection and the best repeatability. And so this can be extremely significant for impurity analysis, as recovery can be correlated to detection at 0.1% level. And this detection covers almost 3 orders of magnitude compared to only 2 orders of magnitudes with conventional systems and columns. And then just because I'm talking about bioanalytical assays, I want to throw some LC-MS analysis in here because that's what typically would be used for detection. And you can see that the trend is quite similar as to what we were looking at the previous slides. So even just moving to the Premier column versus a conventional system solution, we get a 10-fold increase in sensitivity, which is further increased by adding the Premier system, so with the total Acuity Premier solution. And on the right is a nice visual to showcase the improvements in recovery of this phosphorothioate oligonucleotide, where we can go from the green peak to all the way up to the blue peak here. And this is a nice slide to end with, showing the benefits towards bioanalytical LCMS assays. And I'd like to now switch it off to Jacob to show the benefits of the MaxPeak surface technology to peptides.
Okay, thank you, Jen. My name is Jake Kellett, and I'm an associate scientist in the Scientific Operations Group at Waters Corporation. I'll be talking about using Waters Acuity Premier technology for peptide mapping. As Jen mentioned in her review of the MaxPeak Premier technology, peptide mapping techniques deal with the same analyte peak loss due to ionic binding to metals in the LC system. As shown in the chromatograms on the right, the performance results we are all seeking are well-defined, easily distinguishable peaks, particularly for low-level impurities. But in practice, we often get challenging separations where peaks can be broad or exhibit tailing, which can obscure closely eluding low-level peaks. In peptide mapping, where we commonly encounter electron-rich analytes, like those that have phosphate groups, uncharged amines, or deprotonated carboxylic acids, we run into poor performance from absorption phenomena, with surfaces often enough to need to rely on strategies like hardware passivation or high ionic strength mobile phases to achieve our performance expectations. The drawbacks to these solutions are that they require lengthy passivation times or high salt concentrations in mobile phases, which are counterproductive and not always compatible with endpoint detectors, such as mass spectrometers. This absorption issue is particularly evident in RPLC MS-based peptide analyses for acidic peptides, or peptides that exhibit PIs below 7.0 at neutral pH, brought on by the presence of aspartic acid or glutamic acid residues in their sequence. To demonstrate this, we had 3 synthetic peptides manufactured with increasing aspartic acid substitutions in their sequence to increase the acidic character of the peptide. These synthetic peptides were then separated on a conventional LC system with a Waters CSH column using RPLC conditions. As shown on the right side of the slide, the black trace, which represents the peptide with no acidic amino acids, produces a nice Gaussian curve. The blue trace, which represents the peptide with 2 aspartic acid substitutions, exhibits a small increase in peak tailing using the same conditions. Finally, the red trace, which represents the peptide with 4 aspartic acid substitutions, totaling 20% of the peptide sequence, exhibits a marked increase in tailing. Together, these results demonstrate the potential challenges associated with acidic peptides and absorption to metal surfaces. This phenomenon extends beyond synthetic peptides and has practical implications in the biopharmaceutical industry. Peptide-based analyses are an invaluable tool in the characterization and quality control of protein-based therapeutics as part of the quality lifecycle management process. Mass spec-based peptide mapping has also undergone considerable evaluation in development and manufacturing environments to improve productivity and data quality. However, MS-based peptide assays are often deployed with weaker mobile phase additives, such as formic acid, in favor of sensitivity over chromatographic performance. This is an issue in industry where routine assays are expected to perform with consistent and accurate results. But analytical scientists often end up spending an inordinate amount of time on optimizing methods to strike a balance between assay performance and productivity when faced with challenging separations as shown in the chromatogram on the right. Waters Acuity Premier solution addresses these issues in peptide mapping analyses by introduction of a high-performance surface that minimizes absorptive losses of analytes to the metal surfaces of the LC system. As shown in the chromatograms on the bottom of the slide, using the same 3 synthetic peptides from before, the same analysis was carried out on a conventional LC system and on an Acuity Premier system. As noted in the slide, the peptide with 4 aspartic acid substitutions produces a broad peak with a tailing factor of 1.91 on the conventional system, but on our Acuity Premier system, the 3 peptides overlay with each other almost perfectly, with the tailing factor of the most acidic peptide reduced by 42% to a value of 1.10, demonstrating how effectively Acuity Premier technology can minimize analyte surface interaction for increased chromatographic performance. These benefits are gained without sacrificing compatibility with legacy methods built on conventional LC systems. Shown in these chromatograms is Waters' NIST-MAB Digest reference standard, which has been analyzed on a conventional LC system and an Acuity Premier system using Waters' SYNAPT XS mass spectrometer. The high sensitivity of the SYNAPT XS allows us to show that even at a low mass load of 0.2 nanograms on column, a comparable peptide map profile is achieved on the Acuity Premier system using a method developed on a conventional LC system. Taking a closer look at some peptides of interest in the same NIST-MAB Digest standard, we can start to see where the MaxPeak Premier technology makes the greatest difference. We selected 8 peaks labeled in the chromatogram, 7 of which contain acidic residues denoted by the blue arrows, and 1 which contains no acidic residues denoted by the red arrow. The plot on the bottom shows the tailing factors of all detectable peaks for the conventional LC system, shown in orange, and the Acuity Premier system, shown in green. Aside from the 8 peaks of interest, the other peaks tailing factors are calculated at a nominal value of 1.2 for both systems. Peak 12, fragment T14 in the bar plot, was entirely undetected on the conventional system, but was easily identified on the Acuity Premier system. Meanwhile, the basic peak 13, fragment T3, has an isoelectric point of 10.01 and contains no acidic residues and shows no benefit on the Acuity Premier. This clearly implicates the negative ion-rich acidic side chains as a significant contributing factor in adsorption artifacts, and displays how the MaxPeak Premier technology improves performance by preventing the ion-mediated adsorption. Peaks for fragments T1, T22, T37, T4-5, T4, and T7 all contain acidic side chains, and each shows a significant improvement in tailing as well. As shown in the chromatograms on the right, the profile for our non-acidic peak 13, the T3 fragment, is unchanged across both systems, while the acidic peak 31, the T37 fragment, sees a significant improvement to its tailing factor. This reinforces the legacy compatibility of the MaxPeak Premier technology, as peaks that do not see improvement are unaffected, while peaks most detrimental to the chromatographic profile are significantly improved. As mentioned on the previous slide, peak T14 in the NIST-MAB Digest is almost entirely lost to diminished recovery caused by metal analyte adsorption and was therefore of particular interest to us. This experiment was conducted to determine the different performance enhancement contributions of the Acuity Premier column alone run on a conventional system and the full Acuity Premier solution. Shown in the middle plot, a 23-fold increase in detector response for T14 was achieved with the Acuity Premier column alone. As shown in the bottom plot, a 34-fold increase in detector response was observed when using the complete Acuity Premier solution. These observed performance gains are partly attributed to the increased recovery afforded by the Acuity Premier technology, as demonstrated by the area response of the peak for each experiment. Looking on the right, we can see that peak area for peptide T14 increased proportionally with the implementation of Acuity Premier technology, with the greatest improvement achieved when using the Acuity Premier system in conjunction with the Acuity Premier column. The performance improvements just shown for peak T14 naturally translate to improved data quality. Only 3 By fragment ions were detected for the T14 peak using data-independent acquisition analysis when using the conventional system. In contrast, 36 By ions were detected for the same peptide when using the MaxPeak Premier technology. This resulted in a 4% increase in sequence coverage as shown on the right. The missed sequence for peak T14 is highlighted in red for the conventional system data in orange, and that sequence has been identified on the Acuity Premier system shown in green, demonstrating Acuity Premier's ability to enhance data quality for increased confidence in the analysis of biopharmaceutical-based therapeutics. Looking closer at our 6 other peaks of interest in the NIST-MAB digest, which all contain acidic amino acid residues, we see broad applicability to improve the chromatographic profile of these peptides with up to a nearly 81% reduction in tailing factor in the case of peak 31 when comparing data collected using MaxPeak Premier technology to the conventional system. The clinical relevance of these improvements are demonstrated for peak 31 in the case of deamidation impurities associated with MAB-based therapeutics. Deamidation of asparagine to aspartic acid and isoaspartic acid is a common post-translational modification in MABs that has been correlated to drug efficacy. Peak 31, the penny peptide, is of notable interest as it is susceptible to these post-translation modifications, and it contains 4 acidic amino acids. Furthermore, peak 31 sequence is in the constant region of the Fc domain in all humanized MABs, which increases its relevancy as a peptide routinely monitored as a critical quality attribute throughout the biopharmaceutical industry. As shown in the chromatograms on the right, the 80% reduction in peak tailing achieved with the MaxPeak Premier technology allowed us to resolve impurities that would have otherwise been undetected in the conventional system data. Also important to the biopharmaceutical industry is method reproducibility and accuracy, something that is not easily achieved when dealing with adsorption phenomena. In the case of peak 31, fragment T37, the extracted ion chromatogram data shows not only a significant improvement to MS height and area response, but also a significant reduction in the respective relative standard deviations when collected using MaxPeak Premier technology. For triplicate injections, the MaxPeak Premier technology improved assay reproducibility with a 90% reduction in MS height response variability and a 3-fold reduction in MS area response variability. The last point I have to make on clinical relevance is the increased confidence in data afforded by MaxPeak Premier technology. As part of upstream biopharmaceutical production activities, characterization of therapeutics relies on peptide mapping to determine amino acid sequence and related impurities of prospective drug candidates. In this respect, the ability of MaxPeak Premier technology to reduce tailing and resolve critical species of sensitive peptides enables analysts to sequence drug candidates with greater confidence as the spectral complexity is greatly reduced when peaks are well resolved and do not tail into adjacent peaks. Shown is the fragmentation profile of the T37 penny K peptide for the 4 peaks that are related to the T37 peptide, labeled in the upper right inset, with the native peak profile as the bottom chromatographic plot. You can observe that the labeled Y3 ion is unmodified across all 4 peaks, then the Y4 ion is modified only in peak 3 with a plus 0.98 Dalton shift, indicating deamidation. The remaining Y series for peak 3 continue to show a mass shift, indicating deamidation. The Y9 ion on peak 2 shows a shift of plus 0.98 Daltons, again pointing to a deamidation event. The Y9 ion in peak 4 shows a shift of minus 17 Daltons, indicating a succinimide intermediate. This demonstrates the importance of the benefits achieved with MaxPeak Premier technology, which reduced metal-induced tailing artifacts of critical species, allowing for unambiguous assignment of these chromatographically resolved T37 species. Another benefit of the MaxPeak Premier technology is that it makes the acquisition of data faster and more reliable in analyses such as these. As mentioned earlier, passivation techniques using corrosive solvents such as nitric or phosphoric acid are often employed with conventional LCs to stabilize performance. These passivation techniques are often transient and have to be repeated over time. This is demonstrated in the plot on the left, where the tailing factor of the T37 peptide was monitored over the first 40 hours in the system following passivation with phosphoric acid. As shown in the data, when using a conventional LC system, the tailing factor of T37 steadily increases with each injection and does not reach a stable baseline in 40 hours. In contrast, the tailing factor for T37 is not only lower overall, but has reached a steady state from the first injection using MaxPeak Premier technology, allowing users to bypass lengthy passivation procedures. This performance gain is shown to be highly reproducible and consistent. The plot on the right shows the T37 peptide chromatographic performance over 48 hours on an Acuity Premier system. The high reproducibility, as determined by the low relative standard deviation values, enables accurate determination of the relative abundance of the critical impurities. To drive home the message of compatibility, the performance gains delivered by MaxPeak Premier technology can be fully realized by users with minimal to no change in current practices, as shown by this slide. Using the method developed on the conventional LC system, the same NISTMAB digest data were collected on an Acuity Premier system. When comparing the relative retention times of each peak, the scatter plot on the right indicates a strong agreement of peak retention times with a slope of 1.0 and a negligible time offset between the conventional LC system and the system with MaxPeak Premier technology. We can also determine that the selectivity of the profile is not changed on the Acuity Premier, further indicating an ease of method transfer from legacy conventional systems. In summary, Waters Acuity Premier with MaxPeak high-performance surface technology offers a solution to analyte surface absorption. It improves chromatographic performance with benefits to peak shape, tailing, and analyte recovery. Collectively, this study demonstrates Acuity Premier with MaxPeak HPS technology can be broadly applied in the development and manufacturing of new or existing therapeutic drug products. I will now pass the floor to one of Waters' senior scientists, Dr. Xiaoxiao Lu.
Okay, I believe we have seen lots of beautiful results from Jen and Jacob about how many benefits we can achieve by applying the MaxPeak Premier technology to oligo and peptide analysis. Now let's switch our topic to the advanced glycan analysis with Acuity Premier solutions. As one type of the post-translational modification, glycosylation plays an important role in the development of biological drugs. Unlinked glycans, especially those acidic unlinked glycans, are often assigned as critical quality attributes in certain therapeutics because they can affect the stability, efficacy, and immunogenicity. Therefore, we need to carefully characterizing and routinely monitoring those N-glycan profiles during different stages of the drug development. The core analytical platform for N-glycan analysis consists of the GlycoWorks RapidFluor MS N-glycan kit, which enabling a fast and easy-to-use sample preparation workflow. So this workflow is now easily automated on Angel-Plus pipetting robot, allowing biopharmaceutical scientists to improve assay reproducibility and accuracy while minimizing the potential human errors. Pairing with this technology with BioAccord LC-MS system will provide a seamless way to generate high-resolution LC-MS data, which can support the product's characterization, routinely monitoring, and quality assessment. However, while those glycan analysis workflow has been widely adapted by scientists, there are still few challenges in current separation technologies that need to be addressed. Well, the first one is the incomplete recovery of acidic glycans during LC analysis, especially with brand new columns and systems. The second one is the lack of charge-based separation tools for released glycans, which prepared with instant labeling. We heard from our previous speakers, the MaxPeak Premier technology is a great solution to solve the sample loss issue during LC analysis. That is also true for our released glycan analysis. So traditionally, the separation of the released glycans can be done with standard glycan BH amide column. But for using a new conventional column for this application, as shown in this top chromatogram here, without carefully conditioning and passivation, we cannot get a good recovery and separation for all glycan species. The resolution for neutral glycans, as shown in the red trace, looks acceptable, but for most of the silated glycan species, as shown in the blue trace, it cannot be recovered from the non-specific binding to metal surface. As comparison, by utilizing the MaxPeak high-performance surface in the Premier system and glycan columns, it can provide a highly effective surface barrier that prevents the analyst from undergoing undesired interaction with the metallic surface of the chromatographic columns. In this case, as demonstrated in the chromatograms shown below, those problematic acidic glycans could be very well resolved with good recovery at the very first injection with the Premier amide column without any extra conditioning and passivation. Now let's take a close look at difference of the initial performance between conventional and Premier amide column for glycan analysis. And this slide here shows the result for analyzing the released glycan from human IgG using a brand new conventional column. So the initial performance of this column is shown here as the first injection of glycans on column without any conditioning. As we can see, showing in the bottom fluorescence chromatogram here, only 13 of the 19 glycan species can be identified with this conventional column from the injection 1. 5 of the 7 silated glycan species cannot be detected from this initial injection, and the recovery of the most abundant singly silated glycan species F-A2G2S1 was less than 40%. None of those doubly silated glycan species can be detected from this first injection. It was also noticed that a few neutral glycan species also exhibit recovery issue at the first injection on this conventional column. The recovery of FA2, FA2G1, and the FA2G2 is about 95%, 80%, and 60% respectively. So we cannot achieve 100% recovery even for those neutral glycan species from the conventional column. Applying 3 more injections of glycan standard cannot solve this observed recovery issues, as shown in this middle chromatogram. And those problematic glycan species could only be recovered after high mass load injections of Fatune to achieve a conditioning-based passivation. So after this Fatune passivation, all these 19 glycan species, including those doubly silated glycan species, can be successfully detected, which much improved the apparent chromatographic recovery. The effective peak capacity of the conventional steelless column can be improved from 50 to 66 upon conditioning-based passivation. In contrast, with the deployment of MaxPeak Premier technology, the Premier version of the glycan BH amide column can provide excellent chromatographic recovery and peak resolution for all types of glycan species, even at the very first injection without any dependence on column conditioning. So as shown here, all those 19 glycan species can be successfully resolved upon the first injection and run. Impressively, all 7 silated glycan species, including those doubly silated glycan species in the sample, can be detected, even though some are presented with relative abundance as low as 0.5%. Those glycan profiles acquired using those premier version of the amide column were seen to be comparable both before and after conditioning-based Fatune passivation. As demonstrated here, between the injection 1, 4, and 5, the recovery of individual glycans and the effective peak capacity of the separation remain consistent through those 5 injections. It is also worth to mention that the glycan profile achieved using the premier column was comparable to that achieved by using a fully passivated conventional column. So here we show the glycan profiles that achieved using either a fully passivated conventional column or a fully passivated premier column, or a premier column without any passivation at the very first injection. And if we can see from this profile, the profile looks very comparable to each other. And if we calculated for the relative abundance of all these 19 resolved glycan species and calculated for the personality between those 3 glycan profiles, we can see that the personality is less than 8%. This result demonstrates that the MaxPeak Premier technology can help analysts obtain a more accurate glycan profile, and there's no significant effect from the hybrid surface on the resolution or selectivity of the Premier version of the amide column, and the glycan recoveries can be remarkably improved, and the requirements for glycan conditioning upon the first-time usage can be eliminated when using the Premier version of the column. Moreover, the premier glycan amide column can provide more reproducible retention times for silated glycan analysis. The reproducibility was assessed through 4 continuous injections of silated glycan standard on the Fatune passivated conventional and premier column. 3 passivated columns from each column type with the same batch of stationary phase material was used for this study. The retention times and the corresponding percent RSD value was recorded and calculated among 6 most abundant silated glycan species resolved from the test standard using the amide column. So as demonstrated here, the percent RSD of glycan retention times across 3 premier columns was showing at the chromatogram on the bottom were within the range of 0.12 to 0.22%. While this number increased to 1.15 to 1.96% for the same silated glycans when analyzed with these conventional columns. Therefore, with the MaxPeak Premier technology, those Premier version amide column can offer another benefit and provide more reproducible separation for this acidic glycan species. Okay, by applying the Premier technology, it can help us successfully solve the recovery issue during glycan analysis. Now let's move on to the second part of my talk. So how can we do a charge-based separation for glycans? Even though HELIC has been widely adapted for this application, but there's always some feedback from scientists that is asking for a charge-based separation for acidic glycan species, especially for the glycans that labeled with mass spec-sensitive rapid labeling tag like RFMass. To fill this gap, currently we just introduced a new QD Premier glycan C18AX mixed mode column. So this column has all the benefits that we can achieve from the Premier technology. And on top of that, we also have the newly developed mixed mode stationary phase that facilitates us to do a charge-based separation for glycans based on the number of charged residues of each glycan species. So as shown in the bottom chromatogram, the glycans can be grouped by the different number of charge. The non-charged, the singly charged, the doubly charged, and triply charged glycan species can be successfully resolved using our new C18AX mixed mode column. The glycan C18AX column can also provide us with the improved resolution for isomeric acidic glycan species. So for example, the NANA and NGNA are two types of sialic acid found in mammalian cells. Being a non-human form of sialic acid, the level of NGNA need to be carefully monitored during the drug development. However, with only one oxygen difference, it's usually hard to separate these NGNA-containing isomers from the NANA isomers using a simple helix separation. In contrast, as shown in the example here, when we do the separation of fatty glycans using the C18AX column, it can successfully help us to resolve the NGNA variant from the predominant NANA glycan species. And the identification of those two isomers has been confirmed by the high-res mass spec data. In this case, we can see that it has been confirmed that the NGNA isomers will elute in front of the NANA counterparts, so that there is a compelling amount of resolution to help us separate those two isomers using the C18AX mixed mode column. So even though this glycan C18AX column is designed to fill the gap for the charge-based separation for RFMS labeled glycans, we also want to make sure that those columns will not only work for the RFMS derived glycans, but it can also do the charge-based separation for the glycans that labeled with other tags, like the 2AB tags which is commonly used in the released glycan analysis. So here we show the representative chromatograms for separation of both 2AB and RFMS labeled glycans using our C18AX mixed mode column. So as you can see here, due to the slightly weak basicity of the 2AB labels, we believe that the 2AB labeled glycan will have a slightly stronger retention on the stationary phase, which may due to this slightly larger retention time compared with the RFMS labeled glycan. But in general, the profile of those glycans with the two different labels is very comparable. So we can confidently see that the mixed mode column we are introduced here is not only worked for the RFMS labeled glycan, but it's also for the glycans labeled with 2AB tags. So the utility of this new glycan C18AX mixed mode technology is best highlighted through a comparison to other commercially available tools. So as shown here, we do a separation of both 2AB labeled and RFMS labeled fatty glycans using either this glycan C18 mixed mode column or a commercially available alternative columns. So we believe that due to the different design of the stationary phase, the glycan C18AX mixed mode column can provide a much better resolution, as shown here. For the 2AB labeled for both the 2AB and RFMS labeled glycan, the resolution for A3, J3, S3 isomers are all close to 2, while there's almost no resolution for those isomers from the competitor's column. Okay, to summarize the advanced workflow for released glycan analysis, after 30 minutes released N-glycan preparation with GlycoWork RFMS kit, these derivatized glycans can be submitted to a QD Premier system to perform the separation with either a Premier amide or Premier C18AX column. Both the Premier system together with Premier column can help us to achieve a significant improvement for initial performance, recovery, and separation of those released glycan species, especially for acidic glycan species analysis. And finally, that's the end of our talk, and thank you to our audience today for your time and attention and allowing us to share some highlights of MaxPeak Premier for oligopeptide and glycan analysis. With that, we'd like to take any questions that you may have.
Thank you all for that interesting seminar. I hope that everyone listening enjoyed the webinar and found it informative. We'll now move on to the last part of today's webinar, the question and answer session. So we've had a few questions come through here, and the first one we have is, how do the Premier columns compare to bioinert columns, such as those made of titanium?
Thank you. This is Jake Kellett. I'll take that question. So how did Premier columns compare to other bioinert columns like titanium? Titanium columns have the same issues with Lewis base acid interactions as other transition metal columns would, like iron, where they'll interact with free electrons present in the analyte. So we still see issues with non-specific binding taking place when using other bioinert columns that are based on a metal.
Thank you very much, Jacob. Our next question for the group is, do you have Hillock type of Premier columns available?
Currently, we do not have a Premier column for Hillock. However, we have seen benefits of using a conventional Hillock column with the Acuity Premier system when testing cysteine conjugated ADC samples.
Perfect, thank you very much. Our next question asks, do these systems have any other benefits for small molecule analysis? I believe that question may be...
Sorry, I'll take that one.
Thank you.
I was just muting myself. So yes, these systems have benefits towards small molecule analysis. So if you have, it's similar to what we're showing here. If you have acidic small molecules or anything with maybe a negative charge, it can be prone to absorbing onto the surfaces of your healthy system. In particular, we have some examples on nucleotides, as well as there's been some papers released on metabolites and other compounds as well.
Thank you very much for that. Our next question asks, are there advantages of the Premier Tech for SEC and capillary columns, and will they become available if not?
Acuity Premier columns available for size exclusion chromatography, but in the same sense as Hillock, it also sees benefit when running using a conventional SEC column on the Acuity Premier system. And we see benefits to analyte recovery and peak resolution.
Great, thank you, Jacob. We have another question here, which asks, what is the pressure limit for the Premier column and system? And I think that question might be directed towards Jennifer.
Yep. So the system it's similar to the H-class system, so it's a 15,000 psi pressure limit, and then the columns that we have out are, for instance, the 1.7 are typically also the same, so 15,000 psi.
Brilliant, thank you very much. And another question potentially for you, Jennifer, is what type of material has been used to make the hybrid surface?
Yeah, that's a really great question. We can't go too much into detail. I will point out that we have an article in Analytical Chemistry which talks a little bit more about the surface. But what we can say is that this surface is really composed of an ethylene bridge siloxane polymer using a vapor deposition process. And so it's really similar to that of our BEH, so our ethylene bridged hybrid chromatographic particles.
Thank you very much. And our next question is, does the MS probe have to be modified with the new SI capillary or new probe to accommodate the Premier surface technology to reduce non-specific binding in the MS flow path? I'm not sure who wants to have a go at answering that one.
Yeah, this is Jake Kellett. I'll take that question. Currently, there is not an Acuity Premier version of the ESI capillary probe, like the one that you would use to connect a system to a QDA. So there are no modifications necessary to use an Acuity Premier system with an existing MS instrument. but yeah, currently there just are no Acuity Premier versions of those capillaries.
Thank you very much. So we're running towards the end, but we do have time for a few more questions, so feel free to keep submitting them. And our next question is, we see improvements in peak recovery and peak shape, and anything else?
Yeah, I'll take that one. And maybe just before I take this one, just to sort of clarify a previous answer. So we don't have any branded waters, for instance, Helic columns, but we do have a Premier BEH amide column that people can use for Helic separations. So that can be an option if you're doing Helic separations. And then just going on to this question here in terms of peak recovery and peak shape, we do see really great improvements in, of course, reproducibility, especially when we're looking at bioanalytical applications. And some of the more interesting items we've been seeing so far is reductions. For instance, if you're looking at peptides or citric acid, I think we have an app note on this. We have reductions in iron adducts that could be coming from the metal of your columns. And we've also seen, because we have this hybrid surface technology, reductions in any on-column oxidation that might occur as a result of the metal of the column itself. So some really interesting advantages that could happen with these columns.
Thank you, Jennifer. Our next question, this is interesting. So what is the difference between this system and the older H-class bio? How would the H-class bio have performed against this system?
Hi, this is Xiao Xiao. Sorry, Dick. Go ahead.
Sorry about that, Xiao Xiao. I was just going to chime in and say that the H-class bio system is built around the use of the bioinert, quote-unquote, metal, namely MP35N. And this is a nickel cobalt alloy, and it exhibits the same issues as other bioinert metals where there's still free electrons available to interact with analytes. So we would still get non-specific binding interactions on an H-class biosystem if we were dealing with particularly acidic peptides that could interact with those free electrons.
Thank you for that. Xiao Xiao, have you got anything you'd like to add to that, or do you think Jacob covered it?
Yeah, sure. I think Jake covered most of the part, and I just want to comment that when we do the glycan analysis, if we're using a new H-class biosystem, there's almost no recovery for all those problematic glycans. So, but for using the Premier system, since all this metallic surface has been covered, so we can get pretty good recovery using the Premier version of the system.
Thank you both for that. Mm-hmm. Thank you. We've got time to squeeze in a couple more because we've got a lot coming in, so we'll try our best. Our next question is, does the Premier column only work for acidic analytes? And what about tailing basic analytes? So building on your answer, Jacob.
Yeah, so we've seen that the best recovery is experienced by these acidic analytes, and that basic peptides, even those that show tailing, don't necessarily see improvements to their performance using the Acuity Premier system. And that's because the interaction from the basic peptides that are causing the tailing aren't necessarily addressed by this blocking of the non-specific binding interactions.
Thank you very much. I think we've got time to squeeze in just one more question, and that will be, what is actually happening chemically during the conditioning of the column?
Yeah, so this depends on what method you're using to condition your column. If you're running analyte that you're going to be actually looking at as a way to condition your column, you're effectively adding enough sample to cover these exposed sites so that non-specific binding interaction takes place with the analyte that you've used to condition. And the hope is when conditioning that by covering these sites, they will no longer interact with your analyte once you move on to your actual analysis. That's not always shown to be the case, however, with conditioning.
Brilliant. Thank you very much for that answer. Well, apologies, I think that's all we're going to have time for today. I again would like to thank all our speakers for today's informative discussion and presentation, and thank you for everyone joining us online and for your interesting questions. I know I had a lot come in. I hope you found this a worthwhile session. As I say, we've had quite a few questions, and if we didn't manage to get to yours, we'll follow up with you personally. And if you have any additional questions you'd like to ask, please feel free to email me at editor@selectscience.net. If you'd like to listen again to today's webinar or invite a friend to listen, it'll be available on our website shortly. Goodbye, and thank you once again.